Okay, we're talking about threats of tall buildings. Fire is something which is pretty innate to all of us, and we have a natural fear of fire that's kind of built into us. And that's not really helped by people like Hollywood and the such like, who kind of amp up the fire risk. Tall buildings and their risks and the threat to them, well, it's a function of two things: hazard and consequence. Okay? That's how we represent it. That's the professional word for threat, is the word risk. Hazard is to do with the nature of the fire risk, and consequences is to do with what happens afterwards. So when we think about hazard, there's two components to that. How likely is the fire that we're going to face to happen? And then we have the second side of it, which is how big is that fire and what's the smoke going to do arising from that situation. I'm ahead of myself for that. There we go. Okay. Now, the hazard side of it, the potential for smoke and fire to move and spread around a building. In tall buildings, things like atria are a big factor here. These are Soho in Beijing, soon to be the world's tallest atrium. It's a fantastic project. But the problem with atria is that fire and smoke likes to spread up them. Another feature of hazards in tall buildings tends to be things like mixed use. This is the Shard in London. It's a mixture of office, hotel, residential, leisure, everything. You've got different types of fire risk. You've got different types of fire hazard, different probabilities of fires happening, all lumped together. So tall buildings, the hazard tends to come from things like interconnection and the nature of the buildings. Consequence does tend to change with height. We tend to think about the risk of injury or death. And we can also think about the consequences in terms of building loss and in terms of image and the such like changing with tall buildings. They're more high profile. So thinking about things like escape and escape times, if you're in a low-rise building like my office in Manchester there on the right, then the evacuation is simultaneous and very quick, almost instantaneous, you might argue. Then you move to sort of tall buildings like the Gherkin in London. We have phased evacuation, where it takes a bit more time to evacuate the building. When we get to the really tall buildings, you might actually stay in there for the entirety of the fire situation. When we think about the really big threat of tall buildings and we think about fire, we tend to think about structural collapse. So understanding the consequences of structural fire failure is really, really important in tall buildings. But, you know, we don't tend to worry about threats in tall buildings, perhaps because we have building codes. And building codes tell us the building's going to be safe, don't they? You know? We design to the code, the building will be safe. That's a bit of a presumption, I think. There's a few problems with building codes, particularly when it comes to modern tall buildings and the really big super tall stuff. For a start, building codes tend to be a little bit obsessed with your occupancy type. You know, they like to narrow things down. It's a bit like the record store trying to make you think you're a country fan or a rock fan when you like both. You know, tall buildings tend to be mixed use, or a lot of modern tall buildings are mixed use, and building codes are really bad at handling mixed use. They tend to say, well, just assume the worst. Building codes are really bad at refurbishment, or what happens to the building after the day it's been approved. This is Lakanal House in London. Unfortunately, 7 people lost their lives here. It was a residential building that was refurbished to make it better from an environmental point of view, and it made the building spectacularly unsafe. So I think potentially the biggest threat to skyscrapers is building codes. Or following building codes is potentially the biggest threat, particularly to modern skyscrapers. I think particularly assuming that buildings are safe because you follow the building code is where that threat lies. Even worse is when you transplant a building code to somewhere else. This is Mumbai. So what would you assume for your fire service arrival time here? This is not an unusual situation in Mumbai. This is everyday traffic. In fact, probably quite light traffic. There are gaps there that you can fit another couple of cars into. You know. Now we have ways of dealing with these hazards and understanding and modelling them. In tall atria, for example, we do a lot of smoke modelling, which is a very valuable tool for us. We can do that, so we can understand how the fire and the smoke spreads around the building. We can also look at things like evacuation. Sorry, excuse me. And this is a model of an evacuation for a building in Mumbai, trying to understand how lift evacuation, elevator evacuation, improves the evacuation times and reduce the consequences of the fire arising. And we put all that stuff together. We do have tools that allow us to work out what the risk in buildings is. We've got all the basic tools. This is a study by the Building Research Establishment in the UK to understand whether putting sprinklers in a building is a good idea or not, which might sound innate to people from America who put sprinklers in pretty much everything, but in the UK we still don't sprinkler things like high-rise hotels. We don't have to sprinkler anything really apart from high-rise offices and the such like. The problem with using computational modelling and using analyses to answer questions is you put the wrong data in, you get the wrong answers out. And potentially you're no better off than using a building code. We've just criticised building codes for not necessarily looking at the right building type. Same thing happens with analyses. Luckily, there's ways around that as well. So this is very much state of the art in fire engineering now. We started to use probabilistic methods. We don't assume one particular fire. We can assume every fire that might occur in a building under every different design condition. This is from a project in Mumbai where we looked at every different apartment permutation, all this sort of stuff as well. So we can do that. So as I said before, the biggest threat to skyscrapers is believing that codes deliver safety. Trusting in the codes, clinging to them like a child learning to swim clings to a float in the pool. That's a really dangerous thing to do with skyscrapers. But if you move to a performance-based approach, where you're going to prove safety and you think through all the possible permutations and the legacy of the building, then actually that becomes an opportunity for tall buildings. It unlocks tall buildings, it unlocks future potential. So you turn fire safety from a risk, actually, potentially, into an opportunity. Thank you.
What do we see is the biggest threat to skyscrapers? As a structural engineer, I find these projects fascinating, but the reality is that the location, views, and people's willingness to pay for them, that's why these projects happen. So at least my answer to Anthony's philosophical question, what's the biggest threat, and frankly the opportunity, it's economics. So when we talk about buildings, our ability to decide on the materials that are going into them, to model stress and strain, which is what I do as a structural engineer, we're getting pretty good at it. This happens to be looking at a bone femur, and if you pick that geometry, I can do a pretty good job of telling you where to put the material to do the best job to prevent a failure of that bone. Here's the same math applied to a building geometry of a tower. But supply and demand has two different sides to that equation. So as a structural engineer, I control the supply, what goes into the building, but what demands. And that kind of keys a little bit off of what Simon was just talking about. For one, let's start with what's maybe the easiest one, gravity. Fortunately, gravity is the same thing worldwide, and building codes do follow a very similar model on that. So as a structural engineer that works around the globe, my job gets a little easier that we're all talking about the same thing. But gravity, while the math may seem easy, it's actually one of the hardest building challenges to deal with. The math of life safety of gravity is straightforward, but movement with time, creep, shrinkage, foundation settlement, that's actually not so easy. And in fact, what seems like one of the easiest topics to deal with, in fact, is probably one of the costliest that we have to deal with, at least in my realm as a structural engineer. So this is maybe a little bit in Simon's world. When we talk about blast and fire, our challenge here is really limiting the size of the hazard and where the hazard happens. If you can define the hazard, we can probably do a pretty good job in an engineering profession as a way to resist that hazard. But for what man-made hazard? So this is looking at the original World Trade Center towers. After that 767 missile hit on that building, you have a 150-foot wide zone in the middle of that building that is unsupported. Now we'll save why that didn't collapse on impact for a later discussion, but the point is most buildings we design aren't 150 feet wide. And maybe just to emphasize this, so that orange building is maybe a typical office building. That's our office building in Seattle. The gray box, that's the original World Trade Centers, and just the size of a 767, which for a quick argument here, I've scaled to 1.0 for the fuel and the weight that goes in that aircraft. So here's an Airbus A380, same fuel and weight. Point being, we're not going to resist this hazard at the building level. We can, in fact, there are other ways that we deal with this hazard. But when we do talk about blast, for what size hazard and at what location, maybe for the things that are harder to control at the base of a building. And frankly, all buildings, especially the tall buildings, aren't designed to the same thing. Nicole will probably hit on this a little more. Seismic. I'm a West Coast engineer. I do a lot of seismic design. Generally, if on a well-conceived building, we get the building frames pretty well, and we're doing a pretty good job at that. What we really don't do as well on is the infill systems, cladding systems that aren't appropriately jointed. And I actually think the idea of the falling hazard coming off of the building, and especially in developing markets, or unfortunately in markets even in the US that aren't in the high seismic zones of the West Coast, I think this is one of the really big hazards that needs more attention. You know, brick, I love actually brick buildings, but that brick facade on the outside in many countries needs to be very careful in seismic. Wind, I happen to believe in climate change. And you know what, our wind storms are getting bigger as a hazard to our building. This isn't only an increasing event that we need to deal with. Bluntly speaking, I think we do a pretty good job on our buildings for life safety. Our buildings generally aren't going to fall over. We look at 700 and 1700-year windstorms. But facade cladding damage and the resulting water and mold and the economics to try to repair that can do a building in very quickly. So I think wind definitely is a topic that plays a lot into what we do with tall building design, but I think that the hazard is there. A quick side point, if we're talking about resiliency, okay, here is a 3,000-year-old skyscraper. So when we talk about lightning, mold, water, drought, fire, wind, there's probably a lot of lessons here that are still there to learn if we just pay attention and look just at what's around us. So a question I'm always asked, you know, which is worse, wind or seismic? Of course it depends on location, but here's a case study of a tower on the West Coast in a high seismic, moderate wind environment, where for this site and tower at 750 feet, the wind and seismic were pretty close. This graph has on the elevation is feet, overturning moment on the bottom. That same building extruded to 900 feet, wind starts to control at the base of the building. But seismic, due to higher mode effects and the frequency differences of how these behave, actually still controls about 2/3 of the building height. And then if we take that another step farther, up to 1,200 feet, wind is driving the design for sure at the base. But again, because of higher mode vibration effects, seismic is still showing itself in the building. So it really depends on where you are in the building. But again, when you start talking about really tall, slender buildings, the taller we go, this is all looking at life safety. So this is 500+ year events for wind and earthquake. Motion control, and actually looking at the wind, at human perception of motion at the 1 and the 10-year events, the events you're going to frequently see in the building, that starts to control the proportioning of what we put into our buildings. So in a case like this, the size of the core, the size of the concrete is probably stiffness controlled by human perception of motion. The steel inside of it is going to be life safety controlled. So what other ways do we do that? Typically in our buildings, we're going to proportion mass and stiffness for that human perception of motion. The other great strategy is damping systems, and that can be viscoelastic or hydraulic, as some of these systems I'm showing right here that might be more distributed in a building. Or another thing that happens a lot are tuned mass systems that happen up on the roof. So whether it's a water tank or other structures that we can put up there, we can tune the harmonics to settle that. Now, there's still debate on the reliability of these systems for always being there. So in many cases, these systems end up going in for, well, they're there for perception, but not life safety. So bottom line for me, it's economics, because I think most of the issues I've shown there, we can manage the hazard of. With that, I'll turn it over to Hope.
The events of September 11 forever changed the way we design tall buildings in regard to an approach on security and life safety. The design of Tower 1 at the World Trade Center site incorporated advanced life safety systems which exceeded the existing building codes at that time. In 2005, to address security concerns, the building was relocated within the original design of the master plan, away from the public street. This allowed for a public plaza on the west side of the building. This early rendering shows seating along the base of the building, which was eventually eliminated from the final design to avoid having occupants from congregating along the edge of the building. This slide here actually should have been second, is a photo of the master plan. What you're seeing here on the south side is the Vehicular Security Center. And that is basically the key place where all of the trucks and buses that service the underground are reviewed. 7 World Trade Center was the first commercial office building completed in New York City following events of 9/11. There are many security considerations that were incorporated into the design of this building. The barrier seated in front of the middle of the street, blocking both vehicular and pedestrian traffic, was not part of the original design. This stainless steel finished object, with its carefully rounded edges, requires extensive coordination with sidewalk and associated finishes. Following 9/11, such objects started to appear, many without proper approval. At the World Trade Center site, bollards are an integral part of creating the comprehensive secured perimeter for the World Trade Center campus. Don't let what you see at the surface, though, fool you. These 30-inch tall objects, spaced 4 feet on center, are designed to absorb significant impact. Beneath the sidewalk, hidden from the public eye, are robust structures comprised of steel and concrete. Bollards are one of the main security elements that have become part of our standard security protocol for tall buildings. From the site, let me bring you in closer to the building. The structural robustness that you see, otherwise known as hardening, governs the entire base of the building. The first 50 feet of the tower is wrapped with 30-inch thick concrete walls located between each of the tower's perimeter structural steel columns. Sitting directly above the lobby is the low-rise mechanical plant, servicing the 500,000 square feet of below-grade property and lobby. A unitized rain screen allowed for the elimination of conventional mechanical louvers at the face of the building. This was an aesthetic decision, but also a security consideration, as it disguised locations of the intakes for the life safety systems. The variation that you see in the facade also served a dual purpose. First, a design consideration, and second, the variation allows for sufficient air movement for mechanical systems. During the design of the podium wall, a physical life-size mock-up was constructed as proof of concept, as well as an opportunity for us to test out the lighting effect. The use of lighting was an important design feature. There's only 60 feet of linear feet of vision glass in the lobby. So in the absence of having an evening lit lobby, the exterior lighting provides simulation at dusk for pedestrians at grade. To assume optimum egress and providing fighting capacity, extra wide egress stairs were provided, allowing for two-way traffic. Above the lobby, the 2 tower stairs connect to the podium corners, allowing for direct egress to grade. Some of the other enhancements to the project strategy included stair pressurization, photoluminescent markings, and battery backup exit stair lighting. In addition, the project incorporates a fully protected service core. You can refer to the orange box in the middle of the center at the bottom. A dedicated fireman's stair that does not contribute to egress capacity, along with an elevator, a dedicated elevator for fireman use was provided. We're currently standing in the lobby in the ground floor at the core of the building, while the core of the building is under construction. 24-inch thick concrete floors protecting the below grade, cast-in-place walls ranging in thicknesses up to 4 feet, and strengths of concrete walls for the core up to 14,000 psi. One of the main design challenges for this project: how do you design a lobby in the absence of any views to the outside? The security guidelines for the building allowed for only a minimal amount of glass to be used. Therefore, the only natural light is through apertures in the north and south baffled walls located 17 feet above grade. To emulate the feeling of natural light, the interior perimeter walls incorporated 30-foot tall artificial light coats. The design intent to mimic the natural light slots in the baffled walls. You can start to see them along the perimeter right above this art in the back. So on October 29, 2012, Superstorm Sandy took the East Coast by surprise. Like most people, was glued to the TV as a single image of the World Trade Center aired that evening. Water was pouring in. If you're not aware, the existing World Trade Center site includes a bathtub slurry wall which was designed to hold back the water of the Hudson River. By the time Sandy passed over Lower Manhattan, soiled water had filled 3+ levels of the below grade at Tower 1. Once the water got in the bathtub, there was no way for it to get out. With no power in Lower Manhattan, it was days before industrial pumps could get to the site. Only after months of damage assessment could the demolition and subsequent rebuilding begin. A team was put into place to evaluate the site-wide conditions and develop what would become known as an early action plan. First line of defense, identify site-wide vulnerabilities. Second line of defense, protect specific rooms, entryways, stairs, and elevator shafts with watertight doors or removable panels. And the third line of defense, relocate critical infrastructure to a higher elevation. This is one of the photos taken at the World Trade Center site. You can see one of the many openings in the grade plane that were identified as a site-wide vulnerability. So September 11th and Hurricane Sandy have altered the way we design buildings in regard to security, life safety, and resiliency. From the beginning of the design at World Trade Center, it was important to create an environment that speaks of remembrance while maintaining safety. Architects and engineers need to look at the challenges of today as design opportunities and invent ways to create great civic spaces that are secure, safe, and resilient. Thank you.
Hopefully I'm going to throw some alternative thoughts out there beyond maybe the more obvious thoughts that pop into your head when you think, what are the biggest threats to a skyscraper? Of course, the biggest threat is Godzilla. You might laugh, but actually I gave a presentation to my son's 5th grade class the other week, and I said, how can skyscrapers save the world? Thinking they'd think about density and sustainability. One kid thought about this, put his hand up and said, when there's the zombie apocalypse, we can all go and hide in the skyscrapers. Obviously watching too much Walking Dead. So, you know, some of this has been touched on already. So Don talked about gravity and wind effects. I mean, often, you know, the biggest challenge in a tall building is not necessarily that vertical load, but actually, you know, countering the horizontal load through wind and seismic. Now, I put this in quite controversially because I looked for images of towers that had collapsed through seismic, and this was the only image I could find. And actually, if you look at countries that encounter a large seismic earthquake, it's often the low-rise buildings that collapse and not the well-designed modern high-rise buildings. You know, the modern high-rise building can be often the safest place to be inside during an earthquake. You know, fire, Simon talked a lot about fire. The thing I wanted to bring up with fire is there is no consistency around the world. I was in Korea a short while ago and was most intrigued to see a little box strapped to the wall in my hotel room. And I opened this little box and found this abseil belt and brake hammer in event of fire and thought, are you serious? In the event of a fire, you really expect me to rappel down the back of the building? Now, of course, not amongst our illustrious panel here, but professional incompetence. This was a project in China where the pile caps were not connected and they dug a big hole behind the tower and the tower fell over. I feel sorry for the people who live in the identical towers all around it, looking at this collapsed tower, thinking what could happen to our tower. Negative connotation. The president of China 2 years ago came out with this statement, we've got to stop building crazy architecture in China. And all these crazy pieces of architecture got negative connotations. This is the Pants Building. Is anyone going to rent space in that building now? It's been called the Pants Building. This was financial downturns. Don alluded to this. I think this is seriously one of the biggest threats. This building in Caracas was 70% complete in 2008 at the turn of the financial market and became the world's largest high-rise slum. All the homeless people occupied this 70-story tower. China has been lauded for its movement of people from rural to urban, but there are whole cities in China and other places that are absolutely empty. Cities for thousands of people with no people, because they misjudge the market or functional obsolescence. You know, one of the key things that I'm interested in is how long should we design these buildings for? You know, what is the life cycle of these buildings? Because here's a staggering fact. I was here last week in Jeddah, and they're building a kilometer-high tower in the deserts of Saudi Arabia. We have never dismantled a building higher than 186 meters. Other than World Trade Center, which obviously doesn't count. So we're building these buildings, and we have no idea how we're going to take them down. You know, and that was, by the way, it was in 1968 that we dismantled that tower. Terrorism has already been touched on, and of course will be touched on some more this evening. You know, but you know, one of the questions I would ask is really, can you counter terrorism in a single building? I think people have already alluded it tonight. The solutions to terrorism are at a much bigger political, social level, because what concerns me is they're always gonna find a way to attack if that intent to attack is there. And if it isn't at the building scale, then it's going to be at the urban scale. And we're seeing that, you know. How can you counteract people who are willing to, you know, blow themselves up to harm other people? And one of the things that concerns me is that now the boundaries between, you know, what's happening in politics and social and inequality, and we're seeing this civic unrest in cities all around the world that so easily spills over into violence. Pollution. You know, I don't know how many days out of the year people in many Chinese cities get clean air, but it's not as many as it should be. Often the pollution rate is in the order of 5-6 times higher than the safest level. This is a huge threat to our cities and buildings. But here's the key thing that I want to say, presuming you believe in climate change, of course, is that climate change is making all this worse. That's the problem. It's like a cycle that's getting worse. So we can talk about wind and the effect of wind, but actually what we're seeing is the large-scale occurrence of hurricanes. That means more of them, more frequently, in more of what used to be times of the year that they weren't occurring, yeah? In many cities of the world. So it's almost like every day now we're seeing these huge, large-scale natural disasters which are not necessarily natural. Flooding, this is a key one, you know. Cities being wiped out or areas being wiped out for periods of time because of rising seawater, increasing ferocity of wind and tides, wiping out all cities. And as Nicole just showed, once it gets into the building or that area, it's difficult to get it out again. And it's not just the flooding, but what it can impose. Large-scale infrastructure blackouts, lighting, power, transport, all these things. This was caused by Hurricane Sandy. And so my final slide, and a thought that I leave you with, and maybe we can come back to it, is, and maybe this is a little doom and gloom, but I just wonder if we will, well, we won't, but if humanity at some point in the future will see a time where actually we begin to realize that certain cities are unviable. They're unviable because they were founded 200, 300, 400, 500 years ago to a set of conditions which is now completely changed because of climate change and various other things. And actually, when you go back to the most viable part of the city's real viability or sustainability, if you want to call it, it's about its position. And the most sustainable or viable city would be in a location that doesn't get too hot, doesn't get too cold, isn't necessarily in a seismic zone, isn't subject to hurricanes and these things, and is close to natural resources like water. So I wonder, I know it's a radical view, but I wonder whether at some point in 100 or 200 years from now, when we've mopped up Manhattan 10,000 times and it's no longer economically viable, because of course that's the only thing that drives progress in America, sorry I shouldn't have said that, is the financial equation, whether we will see, who knows, the 100, 200 million people city created in a more viable location.
If the issue is that we're concentrating so many people in coastal areas, sea level rise is a real thing, and we have all kinds of infrastructure issues related to that, does anyone think it possible that that skyscrapers could be part of the strategy to protect those cities in the sense of they would be basically raised as almost like a wall around the city? To some minor degree, we're already seeing that with like the project to encircle New York, with parklands that are raised. Obviously, it's a much subtler grade difference, but I guess what I'm picturing is skyscrapers on stilts with infrastructure that is perhaps 10 or 20 stories in the air. How do you make that a viable proposition? Or is it better to just pick up stakes and move inland, you know, to a higher elevation?
obviously World Trade Center was, at that point, it was an existing building. And so there was a lot of, going in and look, like I talked about, trying to figure out like a plan of action to watertight the building. But today, I mean, I'm working on a number of high-rise, and interesting, I'll get to your point about the stilts in a second. But I'm working on a number of high-rises in New York, and resiliency and all the tenants that we're talking to no longer interested in the 100-year floodplain. They're looking at a 500-year floodplain that is basically designed to extremes, but they want to make sure that all of the major infrastructure is happening well above. We're looking at designing with cogeneration plants so that if there was another blackout in New York, that even residential buildings, high-end residential buildings, would remain lit. So I think that people are thinking about it. Everything. I mean, New York City building codes we have to flood-proof our buildings. So there's a lot of infrastructure that's happening. But to answer your question about the stilts, interesting enough, I'm currently involved in a number of projects on the West Side rail yards. And so those projects are actually very interesting because essentially they are buildings on stilts. The railroads are happening below them, so they're buildings without basements. And so these are actually buildings where we kind of have an interesting challenge where we have all of our incoming services are immediately entering and have to go up. And so all of our infrastructure is high up into the building. So I think that actually could become an opportunity to start to look at things like that, is basically taking all of your infrastructure and moving it up high. So I think that that's something that can be addressed in the future.
When you talk about doing these buildings on stilts and so forth, how does that also incorporate the vitality of the cities, which is the street life, the pedestrian mode, so to speak?
There's two major developments happening in New York right now: the Manhattan West and the Hudson Yards site, which is Manhattan West is being developed by Brookfields, and Hudson Yards being developed by Related. The Manhattan West, the platform, the actual plaza is elevated. So there's a major grade change between like 9th Avenue and as you move further west, and so people come in at a sort of lower elevation. So that's basically how it's being handled. So there is, I mean, there's plazas and open park space, but they're happening. Your ground level is basically the level of the platform.
I thought on that one that there's a couple of really interesting high-rises that have recently been built. SOM's doing one in New York right now for Brookfield. 150 North Riverside here in Chicago is another one. My building in Seattle is a Yamasaki Tower done in the mid-'70s, where it's all on a fluted pedestal, where the high-rise is really up in the air. It reminds me a little bit of that tree analogy that I showed you. It's one thing to build a highly resilient building that may be up in the air. It's a skyscraper where it may actually, in fact, be the safe place to go. But if you can open up the ground plane to what it may be more transient infrastructure that's not meant to last as long. And so I'll use maybe some extremes. If you put a tower up in the air, but it opens up the ground plane, it may be down to tents and food court trucks or other very temporary elements that if there's a hazard, it's easier to repair. And there may actually be an easy combination between the two where you can create a great urban fabric down at the base. And if it's subject to a flood or condition, it's easy to come back and fix it. Not everything has to be built to that same standard, but the resilient tower is there to stand for a much, much longer time.
So I would like to take a straw poll amongst this audience of whether you think, let's take San Francisco. So we're all in San Francisco right now. Based on what you've heard and what your belief is, do you see the biggest threat to a skyscraper? So I'm going to ask for a straw poll being one of these three things. Let's call it four things: seismic, fire, terrorism, or other. So please, raise your hands if you think the biggest threat to you living or working on the, let's say, the 60th floor of an iconic tall building in San Francisco. Who thinks that fire is the biggest threat that you would face in that building? Interesting. Who would think seismic? Interesting. Who would think terrorism? Does that mean everyone else, please put your hands so we can see it, thinks other? That means not everybody voted there, but you know, interestingly, that was roughly about equal, wasn't it? Equal, you know, maybe the first two a little bit more.
I answered other, and I actually voted twice, being from Chicago. I think other, and I think it would be all of the above. And one description I've heard of failures is it's a series of common events in a sequence that we have never imagined. So I see these all in silos, and what kind of, I think you're alluding to, is that it's going to be each one of the things that we've talked about in a combination we've never thought of.
I think you're right. And what was going through my mind when I put my hand up for other was thinking about things like maintenance failures, or the guy who doesn't turn up to fix the elevator one day, and then the next day something else doesn't happen because he was double booked, and then you have a fire, and then you have no access at height, all this sort of stuff. You're right, those unexpected combinations. And that's, I think, one of the inherent problems we have with building codes, is they're built on the failures of the past, the stuff that we know has gone wrong before. That's where we tend to design building codes. And then if you're lucky a little bit thinking, but this might happen. But the people who design tall buildings, the people who commission tall buildings, are forever coming up with new ideas for tall buildings. You know, they're very expensive objects. People like them to be unique. They like them to be special. And they're constantly pushing the boundaries in ways that we can't actually predict. And that's where I sort of touched on it very lightly, the idea of using probabilistic methods starts to become quite interesting. We were very concerned working on a project in Mumbai that the building had 4 apartments per floor. So we asked the question, well, is it possible that somebody might buy an entire floor, or even 2 entire floors? And the client straight away said, well, yeah, we've already got people interested in buying entire floors. Now that completely changes the fire dynamic in the building, particularly when you start having multiple floors with people with large apartments joined together between those 2 floors. It completely changes the structural fire challenges associated with that, which is why we went to look at a probabilistic methodology, because that allows us to input all those different variables. Now, admittedly, it is all the ones we can possibly conceive of, but they're inputted as a probabilistic curve, as a normal distribution, and we run every possible combination of those failures and those design solutions to come out with the answers. It's fascinating to do and very interesting. Even better when you model existing buildings applying the same stuff and seeing whether the codes are as robust as people think.
You know, just while you've got the microphone there, Simon, I wanted to ask you, so, you know, something I heard maybe from you even, 10, 15 years ago, and let's be honest, the towering inferno did for tall buildings what Jaws did for sharks. Yeah? Actually, the instances of that happening are not that common. But what I heard, and I think it was from you, is that to begin with, there are not many deaths in high-rise residential fires, far less than in low-rise. Yeah, and the vast majority of deaths in high-rise fires occur through people not believing that they are safe and staying enclosed in their relatively safe enclosure whilst the fire is tackled, but through evacuating and being subject to smoke, not through fire. Is that still correct?
It's still correct, but even in the past few years, we've seen some radical changes happening in particularly residential design. We're already talking to clients about the Airbnb effect. We think of residents in tall buildings knowing their way around the building and knowing how to evacuate. Now, if you don't understand the building, you don't know where the staircases are, then your chance of getting out radically drops. So what happens when you start leasing regular residential buildings to short-term lets? It changes the dynamic of how that building is being used. We saw a similar thing, the Lakenhall House fire that I showed there. That started in an apartment where people were selling beauty products from home on eBay. Okay? So the gig economy, we call it in the UK, let's say the same thing here, where everybody working for themselves, people starting lots of little small businesses on the side from their main job. People start using their homes and their apartments as storage areas for potentially highly flammable materials like hairdressing equipment, hairsprays and stuff like that. So all the fire dynamics that we think about, all the presumptions about that and how people are going to escape are all changing radically, thanks primarily to information technology and the way the world has changed with the internet. So it'll be interesting to see whether that settles down or whether we continue to see new ideas happening, stuff which we just didn't predict a few years ago.
It's funny that you mentioned this, the Towering Inferno, because that was actually filmed in San Francisco where you did your straw poll. But I guess my question is more for the structural engineer. You were talking about basically earthquakes versus the wind. And here in Chicago, for the most part, it's about the wind. But I tend to get questions on tours about, are the buildings designed to withstand earthquakes? And I just tend to say, well, taller buildings are safer anyway. But if we were to have a significant seismic event in this area where you have the New Madrid Fault downstate, wouldn't the tall buildings still be the safest place, even though they might not be designed to the same standards as a building that's engineered for San Francisco or the West Coast? Would it be pretty much similar in terms of safety and life expectancy?
If I was in Chicago and an earthquake was happening, I would run into a tall building. I would. I would stay away from the skin, but I would run into the center of the tall building. The issue of the falling hazard and glass breakage and brick off the outside of the building, that's a real issue, especially in places that aren't designed for the seismic movements. The reality is, though, earthquakes shake like between about 1/10 of a second to a second is the pulses, how fast it shakes. That's kind of about the 8 to 15 story building range. And those are the buildings that absorb all the energy of the earthquake. A tall building may have 7, 8, 9 second harmonics of its moving back and forth. It's kind of like pulling the tablecloth out on a dinner table with all the dishes stained on it. The earthquake comes and goes before the building even knows what really gets going. It may be moving a lot. You may want a seatbelt in the building. But generally, the building's probably going to be pretty safe and not absorb the same amount of energy. So, yeah, I would run into a tall building, but I'd be very careful around the edges of it in Chicago in an earthquake.
I was rather dismayed to see the slide of protesters against the current administration being lumped in with terrorism. I wonder if architects and engineers are really worried about high-rise buildings being targeted by protesters against the current administration. I think those protests are bound to continue for the foreseeable future. And if you are worried, besides public safety or officers doing something about it, is there something that architects and engineers are talking about to protect people who live in such high-rises or work in such high-rises?
I guess I've got to answer that because it was. I'm looking at these guys and none of them are taking it. You know, okay, I didn't put that slide in to make any political, point. I mean, really, if we take it outside America, yeah, there are far larger civic demonstrations happening in cities in Africa and other places which are being directly targeted by terrorists. Really, that's what I'm saying. I'm saying that the subject tonight was about what's the biggest threat to a skyscraper, and really what I tried to do in the second part of my presentation is to say the biggest threat to a skyscraper is not to the skyscraper, it's to the urban realm, it's to the impact of a terrorist bomb going off in the middle of Times Square, cutting the impact on tourism by X amount, and so the link to the civil unrest was purely about the public congregations are happening now all across the world, far more than they ever have done in history. I wasn't saying that everybody who's protesting is a terrorist in any way. I wasn't even trying to make that connection. Apologies if it came out that way.
My question's more structural. I've always been fascinated with 3D printing, and I know 3D printing as far as structures is kind of in its infancy now. I've only seen bridges and single-story houses, things like that. But as far as my understanding goes, 3D printing could print things that conventional things can't construct now. So I'm wondering, if you think your opinion on could you 3D print a skyscraper one day? Safer than we can today. Would it be structurally sound? You could print your fire retardant and things like that easier than we can now.
So a couple of thoughts on that. 3D printing as a technology, could you make a building safer or better?
For less cost.
Or for less cost. You know, I look at 3D printing and a lot of technology, things like that. It's a new tool, it's a toolkit. It's a fabulous new tool. And sometimes I got that shiny new crescent wrench, and man, that's the best crescent wrench I could get. But what I really need is a hammer. You have to use it for the right applications. They are scaling up 3D printing where you can basically be spraying concrete or using concrete. So, and one of our basic building blocks we use in our buildings is concrete. But in that concrete is rebar. And in fact, what really makes that concrete work well is the steel and where we put the steel in it. That's not quite so easy to, one of the challenges of 3D printing is it's one material that generally you're putting out there. And usually, most of our best buildings are a hybrid mix of buildings, of materials to make the structure most efficient. It's not just one material in all conditions. So there's a little bit of, I think there's elements and components that it makes a lot of sense. The whole building idea, I think, is a little bit too far of a reach for kind of a utopian idea, you know, it's magically just gonna happen. And I don't know that you really will end up with the best building answer. But 3D printing parts of buildings, absolutely. And I think that it's a wonderful growth area and some great ideas that can come out of it.
I think you've addressed some of the issues, but let me see if I can frame this right. Every building is a prototype. We've never done it before. And sometimes we're designing them per the current codes or current knowledge. What I fear or am troubled by is what we don't know. Key thing like with earthquakes. In 1971, we learned a lot about the Los Angeles earthquake and eccentric structures and soft first stories. In '89, the steel structures did not perform as expected. And now we're building these twisted buildings, and you addressed it in one of the slides. If it's concrete, what's going to be the long-term creep effects in these twisted buildings? So my question, in a sense you've addressed, is what we don't know right now. And over history, engineers and architects have learned a lot because what they haven't discovered.
It's a great point. You know, we only know what we know. One of the things that Simon touched on that we see a lot in the structural realm is this probabilistic design. Scenario conditions, Monte Carlo simulations, that is the buzz when we're talking about seismic. A lot of times when we're doing a tall tower design, we'll be taking ground records from maybe like 13, 20 different earthquakes, and we'll be running time histories of those, simulating the building performance, and then we'll be trying to look at the statistical average of how this building will behave under those 20 different earthquake simulations. That's still a pretty small sampling of everything that might happen, but I think we're getting a lot better along those lines. We certainly don't know everything. A key to what you've said, though, a lot of design is moving towards capacity-based principles, and especially I'll use in seismic design. We never really know what the earthquake is going to be, how big it's going to be, but what I do know is how the building will fail. And if I can control how the building will fail, which pieces fail first, I can actually create a building that will start to show its problems before it actually collapses, with the hope that you would create a mechanism that people are going to be able to see where damage is happening, be able to get out of the building, or self-identify where the problems are before it actually happens. And that, I think, goes into fire engineering and a lot of other things. So we're getting smarter there. One thing that goes towards what you said, though, when we're putting all of this energy into these tall buildings, there's so much infrastructure material in one place. One of the challenges I have on our building codes is most of our building codes start with a 50-year underpinning. We think about a 50-year design life. And maybe we're looking at a 10% probability in 50 years as a hazard. That might be okay for certain size buildings. I think that's way undershooting the mark for these tall towers. As you mentioned, how often a super tall tower does it actually, have we taken one down? Now, fortunately on structure, we look at very low probabilities for collapse prevention and earthquakes. We look at like a 2% in 50-year earthquake. That's the event that happens maybe once every 2,500 years. So we are looking way out there at a lot bigger events. But I think we should be talking mindsets of 100 years at least. In Europe, that may sound really trite, but something other than a 50-year time frame seems like something we might want to talk about on these biggest infrastructure projects.
I mean, actually, I would add to that. I think we need to design these buildings forever. And if we did that, it would be a completely different mindset, because then you would be designing a building for multiple phases of life, that some of which we don't yet know. I think that's the problem, that we're not, you know, that we are designing, it's 100 years to... Can you ever imagine New York without the Empire State Building? Can you imagine Chicago without Sears Tower? Yeah? Oh, wait, can you imagine Chicago without Trump Tower? Sorry, we're not going political. Sorry, Simon.
I think it's a really, it's a really interesting point, that the big lifetime issue, and also the question about the unknown side of it. We happen to be working on a project in London. It's a ground scraper rather than a skyscraper, but that has a 300-year lifespan. It's for I can't say exactly who, but it's for a very big tech company from this side of the world. And we've been told, well, we haven't designed that building to a building code. We've actually written a building code for the building. We've approached it that way around, because we've no idea what this company's going to be doing in the future. We don't know whether they're going to be building cars, whether they're going to be building spaceships, whatever, in this particular building, whether they're going to be using it just for standard office or call center, or manufacturing stuff using massive 3D printers. You know, we've been asked to imagine, or not to try and imagine everything, but basically allow as much flexibility as possible. And the only way you can do that is to literally, exactly the same way that Don was talking about, understand how the building might fail, and that creates effectively an operational envelope, and then try and communicate how that envelope can then be used in future from a design point of view. But just coming back to the original point and the question that was made, this idea of small changes and such like, and what we don't know, one of the biggest things that I worry about when I see the repetition of projects in developing countries, and it comes back to my point about misapplying codes, is the idea of, well, to the outsider who isn't involved in the building design, two buildings may look identical. I don't imagine there's anybody here who's ever worked on a project with a client and they say, yeah, it's 10 identical buildings. And you know for sure that they are 10 very different buildings that happen to look quite similar in the CGI that was produced at the start. But internally, they will all have their little quirks. You know, they'll move a plant room, they'll move a substation room, there'll be a little bit of dirty ground that changes the structure in one area, etc., etc. And we understand that those small changes can fundamentally change the building. And we work very, very hard to deal with those issues. My concern comes back to your question, your point you made, Anthony, about sort of professional reliability and the professional conduct of some people. If you just cut and paste something somewhere and you haven't thought and don't understand all that embedded history that was in that original design, then there's a great potential to create buildings that are very, very unsafe or inappropriate for their situation.
Okay, I want to switch gears a little bit. I want to ask Nicole. So I think Nicole did a fantastic job of explaining to us some of the measures that were put in place at One World Trade. Exceptional measures, you know, the thickness of the concrete walls, no glass at the ground floor. There are many others, you know, 3 fire stairs, dedicated fireman's lift. So there's many other innovations. But my question to you is, are we ever truly going to be able to make a tall building safe from somebody who is intent on harming the occupants? And really, controversially, should we even be trying?
That's a tough question. I mean, certainly, I am born and raised in New York and was there on 9/11, a couple of blocks away, and you know that was something that definitely crossed my mind after 9/11, and then having been involved both in the 7 World Trade Center and 1 World Trade Center. I think we've come a long way. Certainly, I raised my hand to when you asked your question earlier, that terrorism to me is probably the biggest threat that I see. That is truly somewhat for me the unknown. But there are a lot of, that's why I put the bollard slide in. So there are a lot of measures that people don't even realize that are there. So I think you know, having 4-foot thick concrete walls and using 14,000 PSI concrete is not necessarily the appropriate approach for every single building. I think that you have to look at the potential threat of every building, where it's located. You know, currently working over on the West Side Rail Yards, all of a sudden your box of what your threats are becomes bigger than just sort of your ground plane of who might actually get in, because now you have threats from also from underneath. So I think, you know, one of the things that I've learned, having been working on tall buildings my entire career, all in New York, is that I don't think that you can ever get to a point where you could say that there is no way. I mean, if somebody wants to harm a building, they'll find a way. But I think that certainly over the last, you know, 15 plus years, buildings have definitely gotten safer. There's all kinds of, you know, cameras that people, you know, weren't patrolling. There's, you walk into buildings today, there's security presence, there's parcel screeners. So these look like small measures, but they're actually doing a lot in terms of protecting the buildings. And so I think there's a lot of things that people don't realize. And so tall buildings have become a lot safer. And, you know, Baller, for example, you walk around New York today, they're popping up everywhere. And that's basically trying to protect the, you know, the occupants in the lobbies, and trying to protect either the building or a master plan from car threats. You know, looking at where, you know, fuel oil, like fuel oil intakes, and where trucks might be located. People are hardening, you know, entrances to buildings in terms of loading docks. Security, like the World Trade Center, security actually was happening not inside the building. It's happening well before you actually got to the building. And so you see a lot of those measures happening over and over and over in New York, but, you know, at appropriate scales based on, you know, what the building is that you're building, where it is, and who the tenant is. So if you're doing commercial versus residential, the threats would be very different.
Yeah, I mean, you know, one thing I would add to that, counter to my question, is, you know, when 9/11 happened, many people, even in our network, our members thought it was the death of the tall building. And I can tell you that what has happened around the world since 9/11 has been the exact opposite of that. In the last 15 years, we have seen probably 3, 4, 5 times more tall buildings built in that period than ever existed before that. And actually 9/11 ended up being partly a catalyst. And I think the amazing thing is, unless I'm unaware, I don't think we've ever seen another terrorist attack on a tall building since 9/11. Have we? Not in this country.
Not of that type of scale. You could think about Mumbai, the hotel attacks. But that isn't necessarily an attack on the building as much as it was an attack on the people in the urban, which kind of goes to your point on that.
I apologize for not doing my homework. I didn't think that we were going to have time for a Q&A. Excuse me. A couple weeks ago on YouTube, I found some videos with some architects that are AIA architects who have sort of a conspiracy theory about the whole collapse of the Twin Towers. And I was wondering if you guys could talk about that, something along the lines where the evidence was removed so quickly that it never gave time for any sort of analysis on whether or not the building really was collapsed because of the planes and not other factors such as fuel, maybe, or an inside job or something like that. I tried to do additional research, and it's the only place I could find was on the YouTube, and I couldn't locate any other AIA folk substantiating that.
So I'll, since I'm the one who showed some pictures of the World Trade Center, I'll talk about that for a moment. Take for a moment that initial picture that I put up there, or that second picture I put out there, where I showed the face of the World Trade Center tower, and you had a 150-foot wide zone with 0 column support. 0 columns. The fact that the buildings didn't come down on impact, frankly, left a false perception with many people that we designed these buildings for that kind of a hit, and that the building would be able to stand on impact. Ultimately, so the building was significantly compromised off of that initial hit, and it's in many ways almost an act of God that it didn't come down on impact. Ultimately, but then you had a fire inside happening that was burning twice as hot as a normal fire would be. All the fireproofing had been blown off of any of the materials that it was trying to protect, and you had no water or sprinkler system as a line of defense to try to prevent it. And then they still stood for another hour and a half as they burned. And so it was ultimately the weakening of the steel on the inside, creating failure of the floors, and then a stability condition where it eventually brought them down as a collapse. So as an engineer who understands what they're looking at, it's pretty easy to kind of assess what was there. But I keep coming back to the fact that if, World Trade Centers aside, because I think some very extraordinary measures have happened there, if I look at the normal building we build today, we put a column every 30 feet on center on the outside of the building. World Trade Centers had a column every 2.5 feet on center because they weren't designed with a computer, they were designed with a slide rule, and they weren't optimized to the same degree. And they had a highly redundant system on the outside that in fact was able to span over that wound in a way that most of the buildings we build today wouldn't be able to sustain. So I don't put any credence behind any of the conspiracy theories.
What's been done to existing buildings in all three aspects, terrorism, structural, fire, to reinforce older buildings, to keep them sustained against these new discoveries, new threats we've found?
I think that's an excellent question. I'm going to ask all three of you to answer that, starting with Simon.
I think the refurbishment and the reuse of tall buildings is a really interesting challenge. As Anthony just said, we've had a boom in tall buildings over the last few years. We're only now starting to look at refurbishment and reuse in a whole-scale way of tall buildings in the West. That wave is going to hit almost like a tsunami across parts of the Middle East and such like in a few years' time. It's a really interesting problem and very difficult to deal with. It's quite simple in Europe to some extent because a lot of our buildings aren't sprinklered. So the first thing we often do when we refurbish a high-rise building is put sprinklers in. Americans have been doing it for hundreds of years basically, and we've only really started doing it quite recently, so it's not too difficult for us. The other thing we're very careful about is we went through a wave probably over the last sort of 20 years of putting a lot of highly combustible materials into buildings. The problem at Lakanal House was the addition of, one of the problems was the addition of a combustible insulating material within the facade. We started producing these wonderful materials that are very, very effective at doing their job. However, they burn, and when they burn, they produce some really horrible things as well. So we've kind of learned not to do that so much. So it's a little bit obvious sometimes to say that sort of thing, but yeah, it's selecting the right materials for refurbishment. It's putting things like sprinklers. It's looking at things like pressurization systems, which often are redundant and don't do their job properly, and looking at other ways of doing that. I did a refurbishment of one of the towers at Canary Wharf, which was hit by the IRA back in the early 90s, wasn't it? I think the Canary Wharf bomb. And the whole building kind of went sideways like that. All the glass fell out. All the fire protection that was there, some of it perhaps wasn't, should have been, fell off. All very similar effects to what we saw on 9/11 in that particular case. And the engineer came along and said, well, we had working pressurization systems in this building beforehand. Here's a commissioning certificate. And we looked at it and went, no, you didn't. I'm sorry. Someone just made these numbers up. That they claimed to have been able to pressurize some glazed external staircases that had really leaky glazing in them to start with. And we just looked at it and went, no, this is rubbish. This system never worked. And actually, we repurposed the system. The fans and the ductwork were all still there. And we moved away from a pressurization system with the stair core into an air exchange system in the lobbies, producing a high air exchange, which produced the same effect of protecting staircases from smoke. So we can take systems, we can repurpose them, we can think through all that sort of stuff. So yeah, it's possible to deal with these issues, but it's an interesting, it's a fun challenge. I love doing refurbishment, reuse of buildings. These days we often see a lot of refurbishment happening before the buildings have been built. We almost start redesigning buildings. We've seen this a lot in the UK. We're seeing office buildings being turned into residential buildings on the drawing board, and having to work out how to refit those buildings. Whilst this guy's still pouring concrete foundations.
So the question of refurbishment and are we fixing our older buildings? All buildings are not the same. That's an obvious point. I like a lot of what I see on the West Coast, frankly. And this is maybe where Mother Nature has encouraged us along. That seismic codes have become extremely progressive, and whether it's from an earthquake that's happened or in having seen what happens in earthquakes, there's a lot of trip mechanisms that if you're going to go into a building and extend its useful life, or if you're going to change its purpose and occupancy, the codes will force you or mandate you to go in and do certain life safety upgrades. I think that's a really great standard, and I think there's a lot of activities on the West Coast that have really brought things up. Things like I was showing in the following bricks. You know, infill masonry, unreinforced masonry in a seismic area is against the law in California. There may still be in some buildings, but basically if it hasn't all come out, it's generally coming out or it's been protected in some way. It'd be great to see that in other parts of the country, that we have more mandates that when you're extending the useful life of the building, that certain life safety systems have to be checked. I can speak accurately on the West Coast. I'm not necessarily sure what's everywhere, but I think like what you're describing in London, that's really what needs to be in place, and I think you really have to mandate it at a governing body level, because people aren't going to want to spend the money unless they have to. But when we're extending or repurposing the building, those are the times that those come in.
Go.
So for existing buildings, if I start with life safety, one of the things that came out of 9/11 was the comments were that people couldn't see in the stairs. And so one of the things that came out was that a local law was passed probably about 2 years after 9/11 in New York, Local Law 26, which has now become effective as part of our code. And all buildings that existed over a certain height had to put photoluminescent lighting and battery backup, so that if the power ever went out, there would be a way to get down the building. So that was something that was enforced for all new and existing buildings in New York, which I believe is also part of the IBC. So that was one of the things that came out of it. I would say in terms of safety on existing buildings, you know, obviously infrastructure is there, it's already there, but what you do see is a lot more lobby presence. So things like parcel screening devices, and really that's where if you can stop any kind of event, or that's where you want to stop it, is at a lobby, so that people don't get into a core. And so you'll see that with screening devices, sometimes magnetometers, depending on the project, security cameras, and security presence. And then I would say the last thing in regard to resiliency in existing buildings is that all buildings within a floodplain have early action plans. And so there's watertight doors and a lot of barriers that can be put up outside of buildings to protect your front doors that would happen in case of another hurricane came our way. And the good thing is that typically we have advance notice, and so we have an ability, and so buildings and their managers having the time frame to actually put these things in place.